So thank you. Actually, it's a chapter we published, Gustav. So thanks for this kind introduction. The chapter I will talk about. I named this talk "Hotspot Permafrost: Importance of the permafrost as a major carbon stock." At first, right? But as introduced before, this talk is very close to this report. It's called Permafrost, and it's part of this recarbonizing global soils. And there it's a second volume, hotspots and bright spots of soil organic carbon. So the aim of this talk actually is to give you a better understanding of permafrost as a global relevant carbon storage and the challenges and trends which comes with permafrost carbon mobilization. So to just remind you what is permafrost and why it's a hotspot. So permafrost is ground which is frozen for more than 2 years in a row. But actually the permafrost I am dealing with, we are working on, is much, much older. Lots of it is coming from the last ice age. And actually the permafrost region is the biggest part is located in the northern areas. So it's 21% or 25% of the northern hemisphere. And here you see the map of the permafrost region. There, on the other side, you see where was the highest temperature anomaly last year. So you see this red dot there, and it's exactly on top of this permafrost region. So this region, gets a lot of energy, a lot of temperature put into it, and this, of course, causes problems, right? Yeah. So this actually answers already the question which I'm raising up here. But I just want to show this image why we are interested in permafrost. Permafrost looks like this. Normally it looks like tundra or boreal forest, but if you have the chance to look from the side, you see here the permafrost, and you see the active layer and the vegetation. The active layer actually is a layer where the summer heat is thawing and the winter cold is refreezing it again. So it's a seasonal unfrozen layer. You see the same thing in my sketch there. There's ice in there, there's permafrost, there are unfrozen zones, we call them talik, and there's the active layer on top. Actually, permafrost is thawing, and Gustav said in some regions 70 years faster than expected before. So this puts permafrost at risk, and it causes consequences. The consequences are on every scale. There are local and regional consequences like ecosystem changes, disturbance by geochemical cycles changing, and there are global consequences. The global consequences actually are like the permafrost carbon feedback and the influence on the climate greenhouse gas emissions. Here, just a short reminder that permafrost is at risk. So we see here the 1950s to 2100s development or expected development of the permafrost area in the top 3 meters. And you see 2 scenarios, the 8.5 and the 2.5 scenario. The 8.5 is a current trajectory, and the 2.5 is the mitigation scenario. So when we do something to get the greenhouse gas emissions not that high. Actually, what I want to show here is that even in this 2.5 mitigation scenario, we expect a permafrost area loss of more than 25%. If we follow our trajectory, which is happening right now, we can lose up to 75% of the permafrost area until the end of this century. And if you lose this area, you lose a lot of stuff which is in there, like ice and carbon. So here you see a map of Brown et al. Showing that permafrost contains ice, sometimes a lot of ice, sometimes medium ice, sometimes not that much ice. But actually, my research is focusing also on Yedema deposits, and Yedema is a very special kind of permafrost. It is a very ice-rich permafrost. Up to 80% of this deposit can consist of ice. And moreover, there's a lot of carbon in there, like this peat layers you see in this soil column there. Actually, the Jedoma deposits, the Jedoma area is about 500,000 square kilometers. This is quite a lot of Jedoma out there. And yeah, in general, we have up to 1,600 gigatons of carbon in the permafrost zone. You see this here. And this is a bit less, but nearly twice the amount of carbon which is in the atmosphere. Of course, the atmosphere is gaining every day and every hour, so this comparison lacks right now. But anyway, so there's a lot of carbon in there. And even though it's just 15% of the global soil area, it stores more than 40% of its soil carbon. And in this permafrost area, there's around about 1,000 gigatons frozen in, which is right now not part of the active carbon cycle. It is sequestered, frozen. But as permafrost becomes impermanent with warming, with higher temperatures, and with our scenarios we are talking about, there are processes being able to reactivate this carbon by thaw. And reactivation means greenhouse gas emission in the worst case, right? But actually, why there's so much carbon in the permafrost? So there's not that many plants out there, not that many vegetation on top, compared to the temperate or tropical ecosystems. But like there was a long time and there was low input, long time, and even lower degradation. So this leads to the buildup of a huge stock. So a dynamic stock in general is affected by carbon inputs, carbon stabilization, and destabilization and exports. So input is, like always, plant material. Stabilization in the permafrost is mostly freezing, right? And the destabilization is also very, very unique in this area. I put a sketch right there out of a paper accepted last week in Ambio. So you see here that there is carbon input, these arrows down, there's carbon output, these arrows pointing to the atmosphere. But there's also, if the carbon is like mobilized, it's transported. So there are a lot of ways getting this formerly frozen carbon exported or mobilized. Okay. How is this carbon being mobilized? So this is a photo show of different deep disturbance processes. You see on the upper area there, this is thermal erosion, when there is degradation, and then there's a channel, we call it thermal erosion. There's ice wedge. So ice wedges are these wedge-shaped bodies of ice you saw in the pictures before. If these degrades, then there is like an area which is then looking like this. And this is an area in Churabcha. There was an air strip, and this air strip is right now degrading. Then there's river erosion, there's coastal erosion. And on this picture there, this is the Lena Delta eroding the cliff of Soposise, which is a Jedoma cliff. And also with thaw slumping here, you see this up to 80 meters high wall in the Batagai mega slump in Siberia, which was likely caused by a fire wind or a track of like a road, and then there was like this huge slump being developed. And actually, one of the major processes getting deep carbon activated is thermokarst lakes and thermokarst processes. Here you see an initiating thermokarst lake by ice wedge degradation, and on this the center picture, you see that permafrost is the thermokarst is a local process with the process, but it's actually happening everywhere where there's lots of ice in the permafrost. And this thermocost, as said before, is the key for getting carbon out of the permafrost. So we have this thaw bulb underneath every lake, and this causes year-round unfrozenness of the soil, and there microbes can produce greenhouse gases. When there is no oxygen, also methane, right? And so there's a lot of processes going on. It's all in this caption, but you don't have to read it. There will be a paper out soon explaining everything. The punchline here is thermocost thaws deep, and thermocost causes greenhouse gas emissions. Even when it's draining, when there's no lake anymore, there are still higher greenhouse gas emissions from these areas compared to these areas here, which are undisturbed. So in the FIO report, I wrote something about the potential mechanisms how to get additional carbon into the ground. But for the permafrost region, this is a very unlikely scenario because plant biomass is much, much smaller than soil organic carbon, and future vegetation has, like, because of its size and it's the time, we have a limited capacity to compensate for these emissions we see right now with the thaw. And Gustav talked about peats and wetlands before, and peat, even re-wetting former wetlands, is a process which is very slow. And this paper by Gustav published last year, it shows that even under current projections, we still have an carbon loss from peatlands, a net loss. So these two mechanisms are not able to compensate for the carbon losses we see in this region. And then there's another thing. So we see warming of the permafrost everywhere, and this is from a paper from a colleague, Boris Biscarbon. So they show that 0.4 nearly degrees of warming was per decade was happening from 2008 to 2016. And then the next talk, there will be a lot of projections and future trajectories and emissions. But this paper I cite here, they show that there are loss potential. There's a likely loss between 80 and 650 gigatons of carbon until 2300. So there's a huge loss potential because of warming, and this is also what our models are showing. So direct human agriculture activity has also some impacts on the permafrost, for sure. So there is the use of thermocost basins as pastures and haymaking areas in Yakutia. Of course, this is removing plant material, and there is carbon out of the system in this particular case there. Increased emissions are also there when there are humid grasslands in hot summers. So there is when there's use of the land, there are these grasslands which are temporarily flooded, and then there is CO2 and the methane coming out of it. And if there's an intense use on ice-rich permafrost, we see thaw processes which degrade it so deeply that there is an artificial thermocost lake in this former thermocost, in this now drained thermocost basin. And this has a significant influence on the CH4, so methane emissions. You can see this on these pictures here. So this is a haymaking, Yukechi, Alas in central Yakutia. And this is one of these two intensively used pastures, and then there's water standing there. So what are our ways for minimizing the threats to the soil functions of the permafrost regions? Actually, because it's a huge area, I said before, 25% of the Northern Hemisphere land area, it is not possible to do on-ground interventions. You can't cool such a huge area. So it's not feasible at all. And one of the slogans of this pavilion was, there's no way, so there are no, the melting point of ice does not hear on our negotiations, right? So the only way to minimize the threats for the permafrost region is to reduce our anthropogenic climate pressure. That's the point. Because challenges we face when permafrost is thawing is that they are irreversible on human timescales and also on our ecosystem understanding. Even if we stop right now with our emissions, Gustav said that before, the permafrost region will continue because it's an process we started and the ball is rolling right now, and they keep emitting even if we stop emissions right now. So there are lots of risks and there are lots of challenges to adaptation. And I think overshooting this session topic is a high risk. And we know if we overshoot, this system won't stop if we want to go down with negative emissions at the end. And you see here again this animation of the permafrost carbon feedback. So everything we warm in air temperature will cause more permafrost thaw, which will cause microbial activity, which will cause greenhouse gas emissions. And this again will cause more warming. And so on and so forth. Okay, this is another trend. So we expect, as shown earlier, also in the midterm and long term, more thaw. Here I put a very new animation by a colleague from Avi. You see on this side there, this is the thaw depths 1800, and here you see the thaw depths in 2100. All these dark blue things is the thaw depths of like around 0 to 1 or 2 meters, and all these colors are thaw depths which are deeper than that. And you see the thaw depths like the area here, and on the other side here. So it's going up north. So we see a permafrost pressure, permafrost loss everywhere. And there are unavoidable consequences with that. So there is melting of ground ice. There's the loss of Yiruma areas. That there will be rock falls, or there are rock falls because of unstable permafrost in the mountain areas. But actually, it's not an all or nothing question. If we reduce our emissions, if we reduce our anthropogenic pressure on the climate, this helps to keep as much carbon as possible in the permafrost zone. This is the animation I was talking about. So if you just want to play with everything, this is very cool. It's not published so far, but will be soon. You have temperature, thaw depths, and soil carbon to play with here. And so actually it's very cool. But maybe wait for another few weeks and then you are able to access this. And this leads me to my take-home messages. Thaw and release of just a fraction of the permafrost will cause more warming and will magnify the global warming pressure. And this, of course, will further degrade more permafrost areas, which will then cause more greenhouse gas emissions. And there are processes also remobilizing the deep carbon. So it's not just the carbon in the first 3 meters. It could be up to 20 or 30 meters. And but actually, there's no explosion of this permafrost carbon feedback. It's a continuous process. So there was a change, or there is a change from the Arctic from being a sink to a source, but it's not an explosion. It's continuous, and it will be more in the future, but without any bomb. And actually, it's very unlikely that we can compensate on sites for the losses. But actually, as I said before, it's the overshooting is a very risky thing because this is a slow system keeping on emissions even if we have negative emissions. That's it for now. Thank you very much for listening. And again, if you want to read more, the FAO report is out and it's freely accessible. You can see it there. Thank you. The next